Good morning. Let us start. So this was the last slide last time that we saw. Then we did the calculation. Before we move on, any questions about anything? Good morning. Okay, apparently no questions. Then we evaluated the target standard deviation on the basis of participant results after elimination of outliers. And now one may ask, or one might ask, how big target standard deviation value would still be okay, or is there any way to evaluate how well it went? Yes, there is. So there is something called Horvitz equation. This is an equation that was derived by Sir William Horvitz, who was the founder of this AOAC, Association of Official Analytical Chemists. He examined, as far as I understand, literally thousands of interlaboratory comparison results. And he found that the relative standard deviation of participants, or between lab relative standard deviation, is linked to what is the analyte content in the sample. And interestingly enough, it turned out to be a very general relationship, irrespective of analyte, irrespective of sample type, matrix type. Of course, Horvitz did not observe dots like I have here. These dots are simply generated by the equation. I haven't seen his original cloud of points, but most likely this was a very nebulous cloud. But still, it turns out that the expected standard deviation between participants is pretty well linked to analyte content. Lower is the analyte content. Please note this is a logarithmic scale here. Yeah? Lower is the analyte content, the bigger is the relative standard deviation between participants. He did his work in the second half of the 20th century, I think 60s and 70s. A lot of time has passed since then. And also analytical techniques have become better, instruments have become better, novel sample preparation approaches have been invented, and so on and so forth. So in general, humankind is doing now somewhat better chemical analysis than back then. It would be really strange otherwise, yeah, if it hadn't improved for several decades. Nevertheless, the Horvitz standard deviation is considered as something like what you sort of should get, although these days people typically get lower than that. And on the basis of this Horvitz standard deviation has been defined a parameter called Horvitz ratio, or HORAD. And this is the relative standard deviation between participants in a proficiency testing round that was observed after elimination of outliers again. And this is the Horvitz standard deviation from the same round, taking into account what was the concentration of the analyte. And it is typically considered that if the actual standard deviation is not more than 2 times higher than the Horvitz standard deviation, meaning if the Horvitz ratio is 2 or lower, then we can consider that this was okay. The intercomparison worked pretty well. But if it's higher this indicates that there is some problem in the overall organization of this intercomparison. It is not linked to proficiency tests only, Hurwitz ratio is used also in other types of intercomparisons. The first thing that always can happen is that the samples were not the same. Samples were too different or were unstable so that they partially decomposed. So that different laboratories actually analyze different samples. It also is possible that the labs were really very inexperienced, but it also is possible that the method or methods were not suitable. So this last situation obviously is something that is of great interest if the interlaboratory comparison has its aim to standardize a method, to create a standard method. And this Hurwitz ratio is very good, because if the Hurwitz ratio then is above 2, it also might mean that this method is not really very good. Also, if it is a CRM certification, then if Hurwitz ratio is very big, then one might suspect that maybe the samples were not so stable or were not good. And of course, with proficiency tests, all these things can come into play. So, any questions? Okay, if not, let's move on. Now we finally get into the reporting part. So, correctly made report distributed to all participants is what is absolutely necessary. And of course, all the confidentiality clauses must be respected. And I don't have more about reporting on this slide here. Instead, we will look now at the sample report that had been promised a number of times. And now finally comes the moment. So this is the laboratory comparison that we did together with Verol. Having hard time in such a way that it okay, yeah, we will manage. So first of all, this is the title page, then table of contents, not so interesting. Then the aim, the contacts, everything is given here. The samples have been described. Also links to the previous reports that were produced. Now it is explained how the data treatment was carried out. Case, it was again the Z-score that was the main vehicle for that. And the elimination of outliers was done using the Grubbs test. And now what we also did, which I did not explain to you, the Grubbs test part, what sometimes can happen that very low values don't get eliminated easily with Grubbs test, because they sort of by absolute value do not differ so much from the average. Very high values it eliminates easily. So that we did Grubbs test in two ways. One was simply the usual Grubbs test, but the other one was such that we took logarithms of all values, and then only we carried out the Grubbs test. And that occasionally leads to elimination of some very low values, which otherwise are not eliminated. You consider three values, 1, 10, and 100. Then 1 is different from 10 by 9. 100 is different from 10 by 90. Obviously, if let's assume that 10 is something like an average, then 100 gets kicked off. 1, not necessarily. But on how many times basis, 1 is as much off from 10 as 100 is off from 10. And logarithm will make 1 into 0, 10 into 1, and 100 into 2. So logarithm like compresses the spread on the upper end and expands the spread on the lower end. This is what logarithm does. Here are some other explanations how z-scores are interpreted, etc. And also we carried out pairwise EN number calculations from those lab results that had uncertainties. I will show you later on those tables. And also in one case, we had such a situation that the between sample variability was higher than we wished. So our let's say criterion was that the between sample variability should be more than 5 times lower than between participant variability. Between sample variability, of course, was tested here, yeah. And if between sample variability is high, let's say less than 5 times lower than between participant variability, then we also took between sample variability additionally into account into this EN score. So this is like a modified EN score. Actually, I haven't seen it used like this anywhere else, but in our case we used because we considered it's fair to the participants. But of course, the let's say the definitive data analysis still was the z-score. Pairwise EN numbers were given mostly for information purposes. Here now is the list of participants. Sometimes there happen to be some students in the room from those countries, but this time it seems that Estonia, of course, but otherwise. Yes, you stupid me. Yeah, Poland is represented. So yeah. So this time also there's somebody from this. As you see, it's pretty international actually, although mostly from Europe, but there's one from Morocco, so it's not to be this time a transcontinental. Here now is very interesting. Now here you can see participant results. Moisture content, so you see they vary from something like 165 to 500 something. And again, these are professional laboratories that do oil analysis as their everyday job. Free fatty acids, that's a very difficult one. Here we should not be very much surprised that one has 0.11, the other one 0.02. This is a very difficult parameter. It's very low. Yeah? But moisture is interesting because it's not so very low. Then peroxide value. Peroxide is also a very difficult parameter actually. Then the phosphorus content. This is generally pretty okay, but some values are off. Saponification value is the best. Very good agreement actually between all the laboratories. Here also you see like a very clear demonstration that by far not all laboratories don't determine all parameters. Like for example, phosphorus content out of 22 labs, only 7 did phosphorus content. So that the issue of having sufficient number of labs for statistics is a big issue, yeah, and in this intercomparison certainly is on the low side, yeah, for that. Because from 7 laboratories, not so easy. Okay. Finally, erucic acid content, which also I would say is surprisingly good. Now, yeah, okay. I think I mentioned that moisture content we only take into account for consensus value if it is determined with Karl Fischer titration. So that whoever did loss on drying or loss on heating, then we have put in italics. So that this 500 something and 165, these were obtained using the loss on drying approach, which you see is really not really good. So these were not taken into account for finding the consensus value. What is even more remarkable here, if you look now at this uncertainty, it's K2 uncertainty. First of all, it's given 3 significant digits, which is not really okay. But if you look, the value is 500. K2 uncertainty is 3. It's K2 uncertainty below 1% relative. So they are extremely confident that they are doing very well, and they are more than 100 ppm off from the actual consensus. So first of all, loss on drying is a problematic technique. Yeah, sure, no question. But then they are very self-confident. Another like record-breaking self-confident, of course, is here. If you look at this, it's just mind-blowing how accurate the result is, and it's more than 50 ppm off from the consensus value. So all these red values were eliminated using Grubbs test. Yeah, so all the red values are. What makes for me this kind of document extremely educative is that you see what is really going on in real laboratories, how much they differ, and how massively underestimated uncertainties people sometimes. But then on the other hand, this is, I would say, even too cautious. This value is actually very good. It's not far from the consensus value, and then uncertainty is big. And also, I would say that, like, for example, these two are doing pretty well. Yeah, they actually very close here. Yeah? Of course, it's bizarre to present uncertainty with 4 significant digits. That's a completely different story. But otherwise, we don't have any, we cannot give any, like, any strong critique, to these uncertainties. Okay, perhaps I stop for a moment. Maybe you want to ask something before I continue. This report is in Moodle, as you know, so you all can read it as much as you like. Take the microphone.
The average that appeared there is not the you remove some the labs that use another method, no, like 165 or
So in this case, let me take red color. In this case, what was removed? So what was removed? First of all, completely removed were from consensus value calculation those people who did loss on drying, because we knew that this is not reliable at all. And you see, in this case, we really did it well because loss on drying is completely off, massively off. And then with Grab's test, these two values were additionally eliminated. So that the consensus value that you see down there is the average of the remaining 6 values. You can try to calculate if it makes 391.8, but I think it probably will. At least if you look at it, looks very similar. Yeah, so this is how it's done. In this case, you see all values are in except this one. This has been kicked out. This is explained in the footnote. Yeah. Participating laboratories given random order. Outlying results according to the ordinary Grab's test and Grab's test with log value are marked in red and blue. I think this time we did not have a blue value. Blue are rejected by the logarithmic Grab's test. Yeah, this time there are no, in some rounds we had blue values also, but this time apparently we did not. Red and blue. Coverage factor, yeah, okay, although ppm is not an SI unit, yeah, ppm is identical to milligram. Okay, yeah, these are the other. And here, like erucic acid content, all fine, nobody's picked out. Peroxide value, only one is left out, but you see these remaining ones vary a lot, yeah, from 0.83 to 3.34. A peroxide value is a difficult parameter, yeah, so it's not so surprising. Yeah. And here again, sometimes people have very optimistic uncertainties, like this one. But otherwise, actually, people are doing pretty good job here with uncertainties. And the uncertainties are certainly higher here than relative uncertainties, higher than they tend to be in other places. Phosphorus, this is kicked out, all the others are kicked in. And saponification, nothing is left out. As I said, saponification value in this round was the most successful parameter. All labs did very well. But then again, of course, if you look, these labs, the values are good. There's nothing wrong with the values, but uncertainties are massively underestimated. You look at these uncertainties, these are far below 1% relative. And in most chemical analysis, expanded uncertainty below 1% relative is really, usually you don't get that. Here, these are something like 0.5% relative at K2 level, so it's something like 0.25% relative at standard deviation. I don't. And as you see, this uncertainty range absolutely does not overlap with consensus value. You might also say, hey, wait a minute, but consensus value also might be off. Sure, it can be off. But we can also compare these two values to each other with EN parameter, and you can, even without doing any calculations, I think you see the EN will be massively off, yeah, far above 1. Yeah? So they, again, value-wise, they have actually in very good agreement. These people know how to determine saponification value. There's no problem with that, but they don't know how to evaluate measurement uncertainty. All right, so let's move on. Yeah, these are the values. Yeah. Here are some comments. Yeah, perhaps I'm not going to read all this. This all explains how good and how bad and so on, and how things were done. You know? And here now, you see consensus values and target standard deviations in comparison to previous rounds. This is also pretty interesting thing to look at, because it gives some idea about how well those rounds match to each other. All black data are based on arithmetic mean. Red data are based on median. Yeah? As I think I mentioned somewhere, that we also used median, but as a like a auxiliary or additional information. The definitive values are mean-based values. Yeah? Also, you see that in most cases, means and medians agree very well. There's nothing really wrong with using either of these. So if we want to compare something here, for example, again, let's take the water content. Here the value is this one, the target standard deviation is this one. In the previous round, the value was pretty similar. It's actually very, very similar to that, but target standard deviation was much higher. So in this round, labs did better. Moreover, if you look here, of course, the moisture content or water content was also smaller, but the target standard deviation was same as here. So here it's actually massive. The target standard deviation, 25% of the value. Yeah, so it's huge. Here the target standard deviation is 1.5% of the value. And in some cases, it's actually very similar, like here 0.037, 0.014, 0.036, 0.017. So every fatty acid, very similar, actually. So yeah, let's not stay here for too long, but it's actually useful thing to compare and see how labs are doing over the years.
As you mentioned, like for median, you're not supposed to eliminate the outliers. So what approach did you follow in this?
With median also you can. You certainly can eliminate outliers, because sometimes if there are massive outliers, it can also determine, like if you eliminate 2 from the above, it already makes the median different, because now you take a different value as a median. So in our case, they were eliminated. Yes. This also is in part the reason why mean and median are so similar. Yeah. In our case, they were eliminated. All right, so this is the table. Now we come to the z-scores. So here are participant z-scores. You see they vary widely on the depending on how well the labs did. And you see there are some really good labs here. You know? Like these labs are very good. Lab number 2 is very good. But then there are some really poor labs. Lab number 6 is really has misperformed. Try to determine 3 parameters, and everywhere the z-score is so bad that it's really terrible. That lab probably had quite some explaining to do, to the accreditors back in there. I don't know which one it is, So I cannot. I don't know whether it's accredited also. But if the customers of that lab will ask to see this result, then the lab has a lot of explanation. But otherwise, yeah, this is how it is. And the numbers are different from what they were in the list of participants. So it's not possible to know which.
Ivo, is it possible that the labs that are not accredited to do certain tests, they take part in like interlaboratory comparison or proficiency testing?
Absolutely, yeah. Sure. No, you don't need to be accredited. One of these very goods is Verol itself. Maybe this is Verol, maybe this is Verol. I think Verol did not have any. Yeah, by the way, I think I can actually find out. Verol did not determine erucic acid, and Verol determined many parameters. Yeah, Verol is either this one, and I actually think Verol might be number 2. Verol is actually very, very good. I think they determined everything besides beta-sitosterol and erucic acid, and only these 2 labs are such. University of our Katsekoda, our testing center, also participated. We were organizers, but we also participated, but we did only water. So we are one of these 2, and I cannot say no. We did pretty well. Yeah, okay. On. And now here come the graphs where you can see participant results together with uncertainties, their uncertainties. And now these blue lines are the lines that if lab happens to be between blue lines, then z-score will be below 2. If the lab happens to be between red and blue lines, z-score will be between 2 and 3, or between -2 and -3. And beyond red lines, the z-score will be either below -3 or above +3. And the dotted line stands for median. Yeah, green line is the consensus value. Dotted line stands for median. So you see very good agreement here. Yeah. So in moisture content in general, pretty good. The number of labs actually overestimated, or maybe not overestimated, but were very cautious with their measurement uncertainty. But if we looked at free fatty acid content, the picture is very, very interesting. Yeah, you see they have microscopic uncertainty estimates. Yeah, but labs are all over the place. You see this range from 0.01 to more than 0.06 spread of 6 times. All these labs get z-scores between -2 and +2. Yeah? So all are like, can go back to their accreditors and tell that they know very well how to determine the free fatty acid content. I don't dispute their ability to determine free fatty acid content, but I do dispute their ability to do measurement uncertainty values. This is microscopic uncertainties considering how big is the spread. Okay. Here we have peroxide value. That's a very difficult one, yeah, because peroxide value is the unstable parameter. You may remember for that one, we actually asked to specify the day when they did peroxide value measurement. And again, my critique is not at all that they've gotten very different values, but look at the uncertainty. If you take, like, for example, this lab, you take this lab and this lab, no 2 labs, actually, by the way, this one, out of these 4 labs, no 2 labs are in agreement. Each of these 4 labs is in disagreement with every lab of the remaining 3. This is just terrible. So it's really, really problematic. You might say now, hey, wait a minute, but it's an unstable parameter. Yes, it is. Yeah. Maybe the samples decomposed in time and people measured on different days, and obviously they got different results. Let's check it. We plotted the value against the day when they did measurement. And you see, there's no correlation. So it's not the problem that sample decomposed, it's simply the problem it is a difficult measurement, and measurement-wise it's perhaps okay. You see, peroxide value, let me explain. Peroxide value is the measure of rancidity of oils. It shows how much peroxide has formed on the double bonds. So they tend to form peroxide. And typically it's considered that peroxide value below 10, pretty okay. So there's no question. All these results show that, it's far below 10. So in principle, they all are fit for purpose in the sense that on the basis of all these results, the respective oil manufacturer can say, it's good, it's fine, good, we can sell. But so that measurement-wise, not so bad, but uncertainty valuation-wise. I think peroxide value from something like 20 milliequivalents per kilogram is already, if it's 20 or above, you can already sense that there's something wrong. Phosphorus content, not so many values, but those people who did measurement uncertainty evaluation know how to do, and measurement-wise, also not too bad. And saponification value, here people know how to measure. So you see, also I did not turn your attention to that the scale is different in every case. And here the scale is actually much more like expanded than in other measurements. So actually this range is narrower than in most measurements. And all of them are nicely in here. But then again, of course, if we look at these three labs, each of them is in disagreement with the remaining two. That again, they know how to measure, they don't know how to calculate. Then beta-sitosterol, this was surprisingly good. This is actually a more difficult measurement, but it was surprisingly good, very nice values, and actually hugely overestimated, or let's say very cautious measurement uncertainties. And the erucic acid also not bad, actually. And now here is a lot of explanation about between sample variability. In one case, it was pretty big. Yeah, saponification value and beta-sitosterol, the between sample variability we considered was bigger than we would have wished, so that the modified EN criterion. And now there's the discussion part, which gives some conclusions. That these were good. The high spread of these values were because of free fatty acid and peroxide value was mostly because of the very low values, which makes the measurement very difficult. Then here, free fatty acids, peroxide value, and moisture, the severely underestimated uncertainties, etc. So why we put this like discussion part here is that when participants read it, they say, we know how to measure, but we have to work on our uncertainty. Or, oh boy, we don't even know how to do it. Now come the pairwise comparisons. These are all EN values, and only those labs are included which presented uncertainties. And you see roughly half of these cells are green and roughly half of the yellow, which means that in moisture, most or in many cases, there's disagreement between participants. It's even worse with free fatty acids. It's catastrophic with peroxide value measurement. Most labs do not agree with anybody else, except one lab number 2, which obviously presented very high uncertainty. phosphorus content here, only 2 labs can be compared, but saponification value, that's good. Participants are in pretty good agreement. Also beta-sitosterol, erucic acid, not so bad. Okay, and here come acknowledgement. And here now some annex which explains this median-based data treatment. And now these are the median-based EN numbers now, yeah, which, sorry, yeah, not the median-based EN numbers. Median-based EN numbers were already previously, but these are the EN values calculated on the basis of this median. So here labs can also get some other sense of their results, but not really big difference. That lab which was miserable before is just miserable now. Who was very good before is also good. So big. So, any questions?
For the consensus value, either you can use the median or the mean, but like, what was the criteria of using one or another? Like, I know that the median is less affected by the outliers, but like, what's the criteria?
Why did we use one or the other? When we started in the very beginning, we opted for mean because that was much more common at that time. Median is sort of somewhat more recent invention. And then when we went on, we included median as additional statistic, but we kept mean to be comparable to previous rounds. As I think I mentioned somewhere in the lecture, that if I now would have to start over from the beginning or start some new round, new type of proficiency test, I would do with median, not with mean. Although, good news is that the differences are not so big. So if you look at this, sheet here, it's pretty similar. Let's see if we find something. Okay, maybe we could say that this is maybe somewhat more different. Yeah, actually, it seems that this rejection of outliers has done pretty good job. Yeah, so that the means and medians are fairly similar. So there are no big differences expected. Christian is asking a question. Yeah. In the case the Horvitz ratio failed, value greater than 2, what does it mean when the PT is not successful? How should the PT round proceed when it fails? I don't think it really, like, I don't think it's cancelled or something like that. You see, there's always the possibility that simply participants were not really experienced, or there happens to be a number of really inexperienced participants. Like I gave you an example here, for example, that with very similar consensus values, yeah. Here and here, the standard deviation is more than 3 times different. Yeah? So apparently here in this round, there simply were more inexperienced participants, or they somehow did worse. Does not always mean that the intercomparison round is let's say a failure. I would say it is more problematic if Horvitz ratio is above 2 and if it is a CRM certification or method standardization exercise. Because especially if it's method standardization exercise, and when you invite participants who are known to be good, then probably inexperienced participants cannot really be the issue. It can very well be that the method itself is not robust enough. I would say that if I would run a method, the standardization exercise and the Horvitz ratio above 2, then it would really be necessary to investigate what is wrong. And if it is possible, then actually either start over, just take a new look at the method and do maybe modify it to some extent and do another intercomparison if it is possible. Christian, I'm not sure if I managed to answer your question. Now you write also that I may not catch the explanation previously. What explanation you exactly have in mind? So what is the problem with Horvitz ratio? What kind of what is your question regarding the Horvitz ratio? Okay, you see, I don't have a very clear answer what to do next. As I explained, it's not so clear always. Then let's say the organizers need to sit down and think what to do next. It's not very very clear always. But now, while I was waiting for Christian's explanatory question, a very good idea came. In this intercomparison round, we did not do Horvitz ratios. We did not calculate any Horvitz ratio. But please calculate Horvitz ratios. There are all the data here. Don't do for previous the previous rounds, but just for this one. So here are the values. Here are the standard deviations. From these, you can get the actual relative standard deviations easily. And then from these values, you can calculate how many grams per gram, etc. it will be. You can convert the units. No problem if you do it in an approximate way. Yes, this milliequivalent might be problematic. Milliequivalent actually means atoms of oxygen. It's not O2, but O2 divided by 2. So it's how many moles of something with molar mass 16 is there per kilogram. So this is how you can do. And ppm is milligram per kilogram. As you please at home calculate Horvitz ratios for all these 7 measurements. Let's see how we are doing. We actually did not investigate. Maybe it's very poor, yeah? Christian, I also encourage you to do that, yeah? Yeah, it's mass fraction. Yes, yeah, but you see, milligrams per kilogram can also be done in mass fraction very nicely, yeah, because 1 kilogram is 1 million milligrams, yeah, so you can convert everything into mass fraction. Try to do by tomorrow, then we can, at tomorrow's lecture, we can then see how you did and compare what you got. Yeah, that's actually very interesting. This has not occurred to me on previous years. I've never given this task to students, but this is very interesting. All right, but now, if no more questions, I take back the slides. We now looked at the reporting. And then, like we had COMAR for certified reference materials, there's another database called EPTIS for proficiency tests. So when you will be already in your professional life and looking for proficiency testing, then this is one of the places where you can try to find. It originally, this shortcut EPTIS originally is an abbreviation from European Proficiency Testing Information System, but it's not limited to Europe at all anymore. It has proficiency tests from South America and from China and from all over the world. Yeah, so it's not limited to Europe. Although it is maintained really in Europe, it's maintained by BAM, the Bundesanstalt für Materialforschung und Prüfung. Yeah, I think it is called. So this BAM maintains it. And there you can get all kinds of information. Different proficiency tests give different amount of information. Some even give immediately how much it costs to participate, but some give very little information. Everywhere they say that please inquire, please inquire, please inquire. So as it oftentimes is. I think you will manage beautifully in searching, and so I'm not going to. Now we look at two other types of intercomparisons for certifying certified reference materials and for standardizing analysis methods. So these certifying CRMs we already looked at in the reference material lecture. Yeah. But we still can make some brief discussion here. So the most important differences are here. And we only look in this case, and also in the case of the standardization ILC, we look mostly at differences. So the fact that, okay, you need to prepare samples, they need to be identical, this is all the same. Yeah, this is the same for all the interlaboratory comparisons. Now, the main difference here is that the focus is not how well the participants are doing. So in fact, in this intercomparison, although they may calculate z-scores, they are not really very important. Z-scores are not the aim. While in proficiency test, what the lab participant wants to get back are the z-scores. Yeah, this is why they participate. But here, z-scores are not important. They want to get reference value with reasonably low uncertainty. So this is what is important. And that reference value will actually, by the logic of it, be a consensus value of those expert labs. Yeah? Either average or median, either with rejecting outliers or not, yeah, depending on how people. The second thing here, only expert labs participate. And also here, it is important, or if at all possible, they try to choose participants so that they use different techniques, which I've already repeated so many times. Yes, if it's some elements, then one uses ICP-MS, then we use ICP-OES, maybe somebody is doing XRF, somebody is doing atomic absorption, maybe, I don't know, neutron activation analysis, or maybe something like polarography or like inversion voltammetry, like it's called also stripping voltammetry, electrochemical technique, also possible to do tracer. It's very good if all those different techniques are involved. As we also saw in this acrylamide CRM, there were not so big variety, but there were still many people doing LC, many people doing GC. And sample preparation, if you notice, was very different. Stationary phases were very different in LC, etc. So still there was quite a bit of variability between how participants. It's very good if it's that. Okay. And this is just an example that, okay, if it is polycyclic aromatic hydrocarbons, then the typical way how these are determined is GCMS, but it also can be LC with fluorescence. It's also used. I will say that LCMS, if a suitable stationary phase is used, LCMS also would be possible. Probably not so much used. Also, there is usually a technical discussion where people really discuss the data. If there's an outlying lab, they are trying to find out why the lab is outlying, not just doing Grubbs test and kicking out. They might do Grubbs test eventually, but still they try to find the reason. It is much better if they see, aha, okay, you digest it like this. Yeah, your matrix did not completely decompose. Okay, yeah, we leave you out. But then it's not just statistics, but it is a clear reason why it was left. Much better. Reference value, of course, will be established, and results are usually published, made public. Not always, but oftentimes. Yeah, as you saw, I had these certification reports here and could demonstrate to you. But again, not all CRM producers make their certification reports public. These are the main differences. Well, we've actually seen that part already, so this is why I can be quite fast here. Any questions about this? Apparently not. Okay. But then the other is interlab comparison for validation or standardization of analysis. So if it is a standard method, then you would want it to be as thoroughly investigated as possible, because it will be eventually used by numerous laboratories, maybe not all of them so experienced and so on. So it should be robust, well-functioning method. Meaning, should be carefully validated. And possibly the best way to validate such a method is to organize an intercomparison where all the participants analyze the same samples using the same method. And this is, of course, the same method that is being validated. And Horvitz ratio oftentimes finds used to confirm that method really. If Horvitz ratio is too big, it can be for many things, yeah. But if it's small enough, then it usually means that, okay, the method cannot be very bad if Horvitz ratio is small, yeah. And probably it's pretty good. Now, differences. Perhaps the most important one is this one. They absolutely must use this method. Yeah, otherwise there's no point. Yeah, if you are validating this method, they need to use this. And now it's important because this method might not necessarily be in use in their labs. They might need to first implement it, set it up. This takes time and effort, which makes this also in a way quite costly, or let's say it's a lot of additional work. Because if we go back to the proficiency test, their labs use just the method that they have. And in CRM certification, they also typically use their own methods, which they know for a long time. They know very well how they work. But here they need to set up this new method, which not necessarily new for them, but might be new for them. And also here, typically, it's experienced labs. But the list here is not as restrictive. The reason is that this method that is being standardized will eventually be used by all simple laboratories. So if we now invite here only gurus find, yeah, okay, we can do, oh, well, it works. Then it might be too difficult for ordinary labs. Maybe it needs too high skill level. So it's good to also have here, like, let's say, high-level ordinary labs, not only the guru labs. And also, it is especially good if additionally a group of expert labs can be invited, or they can be actually some of the same labs, who will use some well-established method to get independent reference value, so that the samples that are analyzed with this new method are in parallel analyzed also with a well-known, established, existing method by guru labs, so that people can compare also how well did this new method perform compared to an established and reliable method that is already known from the past. Of course, this all is costly. Yeah? So it's a lot of work. Number of labs to be involved. Every lab wants something to put this work in. Once the intercomparison is over, also here, usually it is a meeting. If anybody is off from all the others, it's not just statistics, but they really want to understand what did the person do wrong, or what did everybody else do wrong. Yeah, it's possibly that this person did everything right, but not very common, but it might happen. And whether that was the fault of the method or some negligence or whatever that might be. You know? And here again, these scores are not really so important, or Ian scores. It's not, they don't really need to like blame labs or you did well, you did not do. That's not so important. The important is to confirm that the method really is suitable for this type of samples, and also comparing with the independent reference value it exists. And also participants are usually allowed to make recommendations. Yeah, we needed to heat this for 30 minutes, but look, it does not really dissolve well with 30 minutes, but when we heat it 45 minutes, it works better. Okay, perhaps we then should make a change into it. Also, as I already mentioned, yeah, outliers typically are not eliminated on the basis of statistics, but they try to find what is. It may well happen that you also, in your future professional life, end up participating in such an intercomparison. So as I said, if you will work in some kind of let's say, commercial lab, you almost certainly will participate in proficiency tests. This is why I'm putting so much emphasis on those. Probably not so likely that you will be doing certification of CRMs, but this kind of like method validation, slightly more likely. Yeah. Most labs also don't do that kind of work, but it is not also not really ruled out. Yeah. So this is my last slide on interlab comparisons. For the materials we have looked also. So from my perspective, we've finished now the second big section of this course, the two tools, CRMs. ILC. But before we move to the third big section, questions, worries. Yeah, let me use the opportunity just to remind you, although I sent it by a message in Moodle, that on Friday there will be lecture. You cannot attend for some reason, then of course it will be recorded so that you can watch the recording after. Yes, I counted weeks and counted days, and yeah, it's better not to put too much like weight on to the end of semester. It's also, I'm slightly afraid that we will not be able to pass all the material, and I need to pick up speed and like do it in a hasty fashion, which I absolutely don't want to give you always time to ask questions and to give myself time to answer them. So, if no, Christian, I think I've answered your thing. Yeah. Yeah. Most likely I did. Yeah. Okay. Okay. No questions. Then we close this and start the next big section, which is about validation and the internal quality control. And we start with validation. Validation is, the slides have been divided into two parts, validation 1 and 2. I have only updated validation 1. Validation 2 I still need to do, but if I look at the clock, most likely on Friday we probably still cannot start with validation. There are some things here that take time. All right. So first of all, some general things. Here are some literature sources. I will explain later, but our validation part in this course does not strictly adhere to any international guideline. I'm rather presenting more general perspective. Yeah? Main principles. I will explain later why not. But if I would point out any guideline, I would probably point out the EURACHEM. So we are sort of maybe closest to the EURACHEM guideline, which has also the very nice thing that it just literally 2 months ago, the newest version came out. Very, very recent, which is very nice. Then I will later on also say something about this thing. Turns out that we've published quite okay, it's our work, but still quite a nice tutorial review on validation specifically of LCMS methods. And also, I very much encourage you to participate in our online course of LCMS method validation, which I think some of you already did. Please raise your hand who did. I think some. Aha, Sarah did. Carlo. Okay, yeah, Christian, yeah, of course, yeah. No problem if you did not. It will run next autumn, and you can participate from your second year university. Those of you who are EEH students, absolutely no problem, because it's online course, and then by the second year you will be sufficiently like educated. Yeah, this autumn you might have been maybe on the difficult side too. Although it focuses on LCMS, and this tutorial review also focuses on LCMS, but both are sufficiently general so that they are also useful for all other techniques. Actually, we are now working already on some, let's say, it's not like formally a follow-up of this tutorial review, but to some extent, yeah. So that we most likely will publish something like that. So now, first, some definitions. There's the eternal like definition diversity. How do you call analytical method? So ISO 17025 says method. But the thing that ISO 17025 calls like measurement method or analytical method in Vim is called procedure. And this Vim definition, how would I put it? The thing that ISO 17025 calls technique is called method in Vim, which like makes it slightly odd, yeah. So that we here use the terminology that we validate methods. In some of my slides, I still have procedure because in the past I used the term procedure. But I've been changing, I may have omitted somewhere or overlooked. So if you see procedure, this is synonymous to method. I started with procedure because Vim says procedure, but labs don't speak that way. And procedure in ISO 17025 is rather an administrative procedure, like how do you carry out internal audits? Yeah, how do you manage non-conforming measurement result and so on and so forth. Yeah. So that we speak about validation of methods. And now, what is method and what is technique? This is also explained here now. Technique is a very general thing, like a generic description. Essentially, if you say HPLC or high performance liquid chromatography with photodiode array detection, this is a technique. Technique can be described literally with 2, 3, or 4 words. But method is a lengthy pages of description. Method specifies measurement conditions, which technique does not. Method specifies scope of application, which technique does not. And method can be validated, and techniques cannot be validated. Cannot validate gas chromatography as such. Yeah? But if you have a gas chromatographic method in your lab, then that one you can. So we try to avoid procedure. We speak of methods and techniques, and method is the like several pages of description, but technique is just a few words. What is the main instrument essentially? That. Now the next thing, what is analytical method validation? It is essentially a process aiming at determining fitness for purpose of an analysis method, meaning whether it does what it is supposed to do. So if it is meant for determining traces of lead in drinking water, yeah, then okay. Does it really enable you to determine traces of lead in drinking water? Is it sufficiently selective so that calcium, magnesium, etc. will not interfere? Does it have sufficiently low limit of detection that you really can reach the low levels, etc.? And validation typically also is a process whereby you determine performance characteristics and also limitations. Again, how low levels can you determine? What potential interference really interfere, which do not interfere, etc. And now the definition of validation is here. It's confirmation through the provision of objective evidence that the requirements for a specific intended use or application have been fulfilled. So what it means, first of all, there have to be some requirements. So you are examining your method against requirements. Requirements can be set by your customer, by legislation, or by the aim of your research project, for example. Suppose you are doing your PhD study and you are determining some trace contaminants in the environment, then the obvious requirement is that limit of detection low enough so that you can actually measure those contaminants. Selectivity good enough so that other different compounds that do not interfere, yeah, and so on. So that the requirements can come from many places. Objective evidence means that you determine what is the limit of detection. You investigate interferences from potential interference. Yeah? If it's lead in drinking water, okay. Does magnesium interfere? No. Good. Calcium? No. Lead, sorry, sodium, etc. And if you have requirements and you manage to get objective evidence, you really can confirm that, yes, good, works well. I can use this method for this purpose. An example is here. Drinking Water Directive of the European Union. Actually, now there's a newer one. Yeah, I have not changed here, but that doesn't really matter much. This directive gives lots of requirements for the analysis methods for determining all those different things that need to be determined in drinking water, starting from like hardness and then pH and then down to organic traces and things. And for most of these parameters, it also gives the requirements for the analysis method. So, for example, cadmium, maximum permissible content is this. And if you want to do cadmium analysis that would really be valid within this legislation framework, your method must meet these criteria. LOD not higher than 0.5 micrograms per liter. Repeatability and trueness, these values, and this repeatability and trueness, they refer to this level. So repeatability and trueness at the level of 5 micrograms per liter. You see, there is no selectivity explicitly mentioned here, but trueness indirectly also accounts for selectivity. So if something really interferes strongly, then at 5 micrograms per liter level, you might get 9 micrograms per liter. Yeah, if the signal comes from something else. That is like indirectly is. Let me stop for a moment. Any questions? Yeah? Okay. Now, and of course, if you look at then these three things, it's only three, and in principle, you should perhaps study something else also. Can you think of any other parameters? We haven't yet looked at those parameters or characteristics, but maybe you can propose. Yeah, true. Robustness, of course, also to some extent is accounted for by trueness and repeatability, but in principle, yes. And then selectivity, of course, which I already mentioned, but also selectivity to some extent is accounted for by trueness. And perhaps linearity and then maybe. Oh, yeah, Christian is also saying linearity and working rate. Good. Now, it is quite common to a clear distinction between method development and method validation. But I would say these two are very closely. Often really difficult to say when one ends and the other one begins. For example, again, if you're developing your method trying to get as low limit of detection as possible, and you use something, okay, not good enough, yeah, now I need to change, I need to concentrate more, maybe take more sample, run through this solid phase extraction cartridge, maybe evaporate to smaller volume. And so you do all those things, and then you again see whether you can determine the very low levels. Then eventually what happens is that when you finish development, you already will have a determined limit of detection. Because otherwise you cannot say that you actually have managed to develop that method at all. So that actually a lot of those characteristics are already determined during method development. But of course, what people often do during validation, they do it like in a more orderly way, maybe more carefully, maybe more replicates, and so on. But different data that you obtain during method development can be also nicely used later as like validation data or used for confirming the validity of the. And now validation, again, as a big picture, can be done either as single lab validation or interlaboratory validation. When you do it at the single laboratory, then of course you do all those typical things. Yeah, you compare to certified reference material for trueness. Yeah, you determine limit of detection and so on and so forth. Yeah. And interlaboratory validation is exactly what we already looked at in the interlab comparison section. So this interlaboratory comparison for standardizing or validation a method, which I explained, and which also, with those of you who are from the EACH program, we have briefly looked in the seminar, these trans fats. This is it. So that in this part of the course, we only look at single lab validation. Also, single lab validation is much more common than interlaboratory. All laboratories have to do that in their own lab, but not so many participate in interlaboratory validation. So that from now on, our work is on, or our scope in this part of the course is on single lab validation. Validation also is very strongly linked to the scope of application of the method. Scope of application determines at least these three things. Which analytes the method is supposed to be used for? What are the types of matrices? And what are the concentration rates? There might be other things such as what uncertainties and so on, but these are absolutely must be there. And if the matrix is different, then you may need either different method or even totally different techniques for determining the same analyte. So the matrix part of this is very, very important. Example here. If it is about determining benzoic acid, which is a preservative, yeah, in a lemonade by HPLC, it's very simple analysis. You essentially can degas and dilute the soft drink and inject it into the HPLC system. Very easy. But the same preservative used also in mayonnaise or in cranberries. Cranberries contain huge amount of benzoic acid. In cranberries, it's not the preservative. Yeah, it's naturally the cranberries generated themselves. Then you need extensive sample pretreatment, extraction, etc., because you cannot inject cranberries or mayonnaise directly into the LC machine. And as I then try to demonstrate, method validation is not separable from the scope of application. So you should, in principle, validate the method within the entire scope of application, meaning separately for every analyte, separately for every matrix, and in every analyte matrix combination at different concentration levels that you may expect. Let's say at least like at low and high concentration, or sometimes low, medium, and high concentration. So in principle, this is what has to be done. Of course, this type of validation might often be too work intensive, so that when you develop your method, then you need to put so long time into validation, and still you cannot offer any services to anybody, that it sometimes might not like make sense like this. Let me give you an example of this. Suppose you are a food control laboratory, and one of your tasks is to analyze pesticides in fruits and vegetables. There are literally tens of different pesticides that are currently in use worldwide. Pesticides have like very different purposes, but let's say preservation pesticides and perhaps residues of herbicides or insecticides might all come into play. There are maybe something like 30, 40 that should be considered. Then in this country, if you go to a shop, you find probably something like 50 or 60 varieties of fruits and vegetables. Start with potatoes and carrots and end with something. Mangoes and what is not really very common here, but still safe. And if you now take, let's say that there's 40 pesticides and 50 fruits and vegetables, it makes 2,000 analyte matrix combinations. If for every of those you would like to do at low and high level, this makes 4,000 analyte matrix concentration combinations. Yeah, it's quite some validation. Yeah, so it's usually not doable like this, that you really manage to investigate everything. So what people typically do then, let me also say that this lab, that is food safety lab, they don't know what will be brought to them. Today it might be grape. Next day it might turn out that, okay, some suspicious lot of bananas has entered European Union. Now we all need to check whether these bananas are okay. Then the next day it might be orange, and every day it might be also a different pesticide. So they don't know what they will get. They will get different fruits and vegetables. So what they usually do in that case, they do what we looked at in the CRM part with matrices. Remember, there were the commodities and commodity groups and things. They pick something which is the most common, like orange, of course, and potato, maybe cucumber, and they do the validation with those and with the most common pesticides, so that they already can start working. Most samples that come into the lab, they can already manage. If comes a sample, this we haven't validated, then they either quickly do something so that they see that it more or less works, or even maybe reject the sample. So that compromises are often necessary. So it is often not possible to do beforehand all that you need. But here is my favorite sentence. Never stop. Okay, you managed to do your main analytes and matrices. Always find possibility to include more matrices or more analytes and so on. So that, okay, potato and apple and cucumber and grape are the most common, but sometimes you also get carrots where you need them, okay, then you, at first possible moment, you also include carrots, do the carrot validation with pesticides which are relevant there, then maybe it turns out that, I don't know, peaches oftentimes contain some nasty pesticides. Then you put peaches. So you can start with little, but never feel that, oh, now I've done all. Good, good, good. Now I don't validate anything ever. This is not a good idea. We will later on see that actually even those things that you've already done determine the parameters. It's a very useful thing to occasionally redetermine, especially with some of them. Aha, it's 11:45 unexpectedly, huh? So, okay. But here we start with performance characteristics. It's actually is a very good place to stop here. Yeah? So we stop and we continue from here next time. Yeah. So if no further questions now, then thank you, and we will continue tomorrow.